So we'll start with this constraint and generalized coordinates. I usually don't rush with any topic. I don't prefer that. We'll go a bit slow. And what I'm going to talk about today is something which you might have already done a bit before. But then this is a part of the syllabus. This is the first unit. So everywhere the first unit starts with very basic. So we are going to start with generalized coordinate and constraint. So before I really go into constraint, I'll just give you a brief idea, or I think you already have that idea of the coordinate system that we are actually going to use. So the unit, the first unit, and then as I said yesterday, you will have different topics here, and going to about constraint and what are constraint, what are the types of constraint. We are going to take some examples of constraint, and if time permits, we are also going to solve some examples. How do you solve it in a class in this kind of scenario in an online class? What I'm going to do is I'm going to write down a question on the slide, and it will be there displayed for you, and then you are going to take a page and a pen in your desk there, okay, and then you can solve it, okay. I don't mind whether you look into your mobile screen or your laptop or desktop screen, but I preferably it should be a laptop or desktop screen so that you can manage it properly. But I do understand that everyone might not be having the access to a laptop or desktop all the time. So it's perfectly fine. But please keep a pen and a paper with you. Sit in a proper position so that you can sit and solve problems, so that it will give you a good feel of having a real class. Okay, this is not the way we wanted to start, but anyway. So I'll give the question, and then you can actually solve, and then probably I'll give you 10 minutes, and then you can try, and then I'll ask for someone to give me an answer, and then that person answers, and then I can share what is the answer look like. Okay. So you are not a PG UG student, you are PG student, so it's serious enough to understand that you need to solve your own problems, right? Real life thing. Next, we are going to talk about virtual work. So virtual work is something which is something which is producing minimum displacement, okay, and then the resultant virtual work is always going to be more or less zero. This is something which you are going to see. Some principles are there. And then we are going to talk about generalized coordinates. So a very brief of that would be, if you are talking about coordinate system, if you are going to solve down an equation, let's say a mathematical equation, if there are more and more variables, it becomes more and more complicated. For example, you want to solve for a variable, let's say x and y, and now there are two variables. Now you cannot solve two variable equation using only one equation, right? You cannot solve two variable using one equation. You need two equations. So it becomes more. And if you have more coordinate, it becomes more and more, and then the more number of equation, more complication mathematically, and so on. So this idea of generalized coordinate is actually to reduce the dependent coordinates. Okay, so what happens is we can actually have the number of coordinates for which we need to solve will be lesser in number. If it is lesser, the number of equation becomes less, and then the solution becomes simpler. And that is the main motto of this particular topic. And based on this, we also have something which is called the D'Alembert's principle. Okay, so we are going to look into all these aspects, and then I have seen there are some UG syllabus which actually already talks about these things. But anyway, so that we are on the same page, and since this is in the syllabus, we are going to do it. Okay. So the first thing is position coordinates, and I think position coordinate is something which all of us are sure, but the thing is sometimes we get a bit confused on how to represent it. Okay, so what happens is, let's say I want to actually have a coordinate system, and then please remember, in real life you don't have a two-dimensional system. Most of the time it will be three-dimensional, right? That we need to actually establish facts for three-dimensional picture also. That's very important. Okay, so what we are going to do is we are going to understand first what is position coordinate and how we are going to use it in classical mechanics. So in general, when I say that there is a, let's say, a point here, and you know that this is your x-axis and this is your y-axis, and then you can actually represent it by two coordinates, let's say x1 and x2. So this is something which you already know, which is simple. And then let's say this is your origin, right, 0, 0. So what is position coordinate is, you can actually draw a straight line from this particular point to this particular point. Okay, let's say this is the point. Okay, and then that will be actually represented by a vector which is r1, right, or r1 bar should be represented by a vector. And then we know that if you actually drop a perpendicular here, this particular thing would be nothing but, sorry, let me just write it down as x1 y1, not x1 x2. So this particular coordinate would be nothing but y1, and this particular position would be nothing but x1. So this is how it is represented. Now if you want to represent it in the vector form, we already know how do we do it. We simply write it down as R1 bar is equal to, what is the magnitude along the x-axis, that is x1, and then this is along the x-axis, so we always represent it by a unit vector, and then what is the representation or the magnitude along the y-axis, that's y1, and then we will actually represent it by the j vector. And then if you consider a three-dimensional picture, the k vector, the k cap comes, right? So this is basically nothing but what we call as position vector. Now how do we represent it in a different way? Now this is nothing but Cartesian coordinate, we already know. And then you know, when you come to more complicated geometry, it becomes difficult to represent everything by a Cartesian coordinate. So what happens is we need some other kind of representation. So here what I can do is I can simply represent it by this r, which is the position vector, which can be written in terms of x1 and y1. But if we know r, we know what is the position vector, and we can also represent it in terms of theta, right? So that means now if I want to represent this particular point, let's say P, we can represent it in terms of r and theta. So theta will actually represent something like the inclination of this particular point with respect to the position coordinate, okay? And this is something which we already know are called the polar coordinates. So polar coordinates. So it depends on what kind of system you are considering, but I think these ideas needs to be very clear, that what are polar coordinates, what are Cartesian coordinates, okay? And then if you basically consider something like r, theta, and you go to the third dimension and you consider phi, you basically consider the spherical polar coordinate. So this is a spherical polar coordinate, okay? So I think this is important, and then this is something which we already know. But then in classical mechanics, what happens is these kind of ideas have more and more applications, because when you go to more and more complicated system, you need more and more coordinates. So I don't want to use so many coordinates because it becomes mathematically very difficult. So what we do is we usually reduce the number of coordinates, and for reduction of coordinate, we should have a very clear picture of Cartesian system, polar coordinate system, spherical polar coordinate system. So that is why I just started with this slide, okay, rather than just directly going or jumping into the definition of constraint. So then let's talk about constraint now. And then if I go for the definition, I think it's very simple, that you have a system moving here and there. You restrict the system to move, and then there basically it is nothing but a constraint system. So in general, if you consider, let's say I have a circle, right? So you basically have a circle, okay, and then this is the center, and then you are moving along this direction. You are not allowed to leave the path, okay? Might be you are on a let's say on a drive, okay, on a driveway which is having a circular path. You're not going to leave this driveway. That means your motion is more or less constrained, okay? You don't have any motion along the z-axis because you are not going to fly if you are driving. If you are flying, then z-axis comes into picture. So basically moving on the xy axis, and then also that is restricted, okay? It's moving in a circular motion. So if you simply want to represent your motion, you can simply say that x square plus y square is equal to r square, or a square, radius, right? So then if we just say that this is r, that means this r is fixed. So that means your distance from the center is fixed. And that is what is constraint is all about. It is very much a dictionary meaning, constraint, okay? Nothing too much physics about the meaning, at least, okay? It's nothing but the restrictions that has been put on the motion, and that is something which we call as a constraint. So at any instant, if I want to know what is my position, I should know the coordinate x and y, simply put it there, and then actually I know what is my exact position, right? So I think that is very simple idea, very simple concept. If you go a bit deeper and then try to understand it in a more complicated system, we do say, I think this is also there. This is also something which is coming under part of general physics. You have this, and then you have this, let's say a box which is placed on this sledge, okay? And this sledge is making an angle with theta with the horizontal. And then if you want to find out the different forces acting on it, you know that this is your mg, okay? And then this is your normal, which is the reaction offered by the sledge, okay, the normal reaction. And then you can actually say that this is actually sliding down, okay, and then let's say it might be having a force acting on it, and because it is sliding down, there is a frictional force which might act opposite to it if it is not a smooth surface. Now why I am saying this, okay, why I am explaining this, The simple reason is, suppose it's a frictionless surface, then this force will actually vanish. So then that the equation becomes a bit simpler, okay? But then if it's a frictional surface, then this F friction comes into picture, and then you should know what is coefficient of static friction and all those factors, and then you basically solve the problem. But then whenever you solve these kind of equations or these kind of free body diagram problems, you usually consider the x and the y axis. The box is not flying, it is not coming out of the plane of the paper or plane of this screen or going into the plane of the screen. That means there is no z-axis as such. But then imagine if there is z-axis, then it will be very difficult to actually solve this. It will become more complicated. Okay, of course everything is solvable, but then it will become more complicated. So that means this is also an example of constrained motion. So whatever example you take, most of the times you will see that there is one or the other constraint imposed on it. You need to analyze it mathematically. That means you need to know what are the dependencies of the coordinates. Let's say, for example, you have a system where you have gas molecules within a box, within a cylinder, let's say. Now it's very difficult to mathematically describe the motion of that gas molecule, because it will be random. But then again it is constant because it is within the cylinder. It is not allowed to move freely outside. Okay, so it depends on what frame of reference you are considering. Anything around us is more or less constrained. Depends, like the air molecules which is there around you. You might say no, this is not constant, but it depends how are you considering it. Are you considering it inside the jar? Are you considering it inside the room, or are you considering it within the atmosphere? If you're escaping the atmosphere, then that's a different thing altogether. So the broadness of this is totally different, okay? But then we are going to restrict it, and only we are going to study few specific problems, okay? Few specific types of constraint, few specific mathematical understanding of constraint, and so on. So the first thing and the first technical term that we are going to come across is holonomic constraint. So if you were going to write down that equation where a person is moving in a circular path, simply write down x square plus y square is equal to a square. So that is the equation. Okay. So if you can represent anything mathematically using an equation, the first part of your calculation is done, and that should be done correctly. Okay, so it is very important. So whenever we are basically considering anything in the form of an equation which depends on different variables, for example, let's say it depends on x, okay, it depends on y, it depends on time, it depends on z, and so on. Okay, it depends on these factors, and then you can write it down in the form of an equation. For example, the motion in a circle. Okay, so these are all nothing but examples of holonomic constraint. So they can be expressed as a function of coordinate and time. Very important. Okay. So we have this function r1 r2 t is equal to 0. So the circle example that I have given, you can say that this is nothing but a function of x, okay, and y. Okay, and that is equal to, let's say, you can write it down as a square, no problem. You can write it down as 0, because you see that a is a constant, so a doesn't vary, so you can just simply write it down as this. Okay, now what is the form of the function will depend on the path that it follows. So if it's a circular path, the form of the function will be different and so on. So this is a very simple idea. So this doesn't depend on time, but in general, when we talk about holonomic constant, this depends on time. So it might depend on time, it might not depend on time, more or less comes under the broad category of holonomic constant. So question for your exam might be, what are holonomic constraint? Give an example. Okay, so you can just explain this, you can write down this equation, and probably this won't go beyond 2 marks. Okay, and then you can give an example of a rigid body. So if a rigid body is not allowed to move everywhere, okay, then this is basically nothing but can be defined in this kind of equation. So imagine this, you have one point here ri and one point here rj. Okay, and then you can do the vector addition. So you see this goes rj, and then this is rij. Okay, so you can write it down as rj plus rij is equivalent to ri, right? Because this is also important again, ri can be written as rj plus rij. Very simple, right? So this is that. Now you see this, if you look into this particular term, this is actually a vector, okay. Please note in your books and all, sometimes they do mention this as bold. So if it is bold means it's a vector, okay, as in this diagram, but in general, when we write it down a copy, we usually don't darken it, just put a bar there. So we have this, so Rij can be written as Ri minus Rj, okay? So Ri minus Rj, okay. So that means what you can do is, we can actually represent this rigid body in this form, okay. Don't worry about this equation. We have different examples, different equations altogether. This is just a very simple equation that we are explaining here, okay. So that means this particular vector Rij, okay, Rij will actually depend on what is the position vector at the end and what is the position vector at the beginning, okay. So this is just an example. You can give any example, okay, not this example. You can give any example for holonomic constant. The only thing is it should be expressed in the form of an equation. So even if you explain a circular motion, I think that is perfectly fine. We're going to go into more complicated problems, so don't worry. Next we have got something which we call as the non-holonomic constant. So we cannot write it down in the form of equal to 0. You can of course write it down in the form of greater than or less than, okay. So if you consider a gas in a container, that is actually an example, a good example of holonomic constraint. And then we can talk about object rolling on a surface without slipping, okay. Now why this is a non-holonomic constraint, this is a food for thought which I'd like all of you to think about, okay. Object rolling on a rough surface without slipping, okay. So why this is a non-holonomic constraint, probably I'll ask you in the next class tomorrow, okay. Think about it. Question again, non-holonomic constraint cannot be expressed in the form of an equation like f xy is equal to 0 or f r1 r2 t is equal to 0. It basically, a good example would be gas inside a container. And then if you consider an object rolling on a rough surface without slipping, that will also be an example of non-holonomic constraint. Now why this is non-holonomic is something which I'll ask you tomorrow. You can think about it, okay. Don't write down anything. This is not an assignment, not an homework, just to generate interest in physics, okay, or classical mechanics in general. So there are another two more types of constraint which are important. This is just a subcategory. Sometimes it doesn't depend on time, okay. So if it does not depend on time, we basically call it as scleronomous constraint. And then if it depends on time explicitly, directly depends on time, it basically be called as a Renomous constraint. So there are two types of constraint, the Renomous constraint and the scleronomous constraint, okay. So this is again there. But then you might ask me a question, can holonomic constraint be Renomous? Yes, it can be. If we consider this example, this is a holonomic constant and it is Renomous because it depends on time. And can it be scleronomous? Again, yes, true. This is a holonomic constant and it does not depend on time. So this is nothing but scleronomous, okay. So this is there. So this is a simple idea, and then I think these are basic definitions here. So the exam question might be, what are the different types of constraint? And then you can answer holonomic constraint, non-holonomic constraint, and then if you subcategorize it, you write down Renomous and scleronomous constraint. Please remember for your exam, these questions will be more or less an objective type. So it will be 2 marks question mostly. And if you're writing it down, write it down in a proper way so that everyone understands, okay. So this has been a problem with many students, okay, when they are in PG, okay, they think, or even in UG or even in school, sometimes you write down an answer thinking that the teacher already knows this. If I write down a notation, the teacher will understand this. See, the teacher knows, that's why he has taught you. But the thing is, you have to write it in such a way so that if someone doesn't know, understands what you have written. That is very important, okay. So please be expressive in your answer scripts, okay, important. Don't waste too much time, do justice to the mark. If it's 2 marks question, don't go for a 2-page answer, and if it is 10 marks question, don't go for a half-page answer. I think that is not suggestive. Okay, so what are the difficulties in constraint, okay, what are the issues that actually comes in, okay. So then if you consider a constraint, the individual coordinates Ri are no longer independent. So the example that we have seen, let's say this example, maybe we can take this example here, this particular diagram we can consider. This Ri is actually not independent. It depends on Rj and it depends on Rij. Imagine this Rj is not here, it's shifting. Let's say it goes here. this particular position, and then this goes here. So then this is going to affect the value of Ri, okay, the magnitude of Ri. So this is no more independent, it has actually become a dependent part, okay. So what happens is actually in general, the equation of motion for the individual particles are now coupled. So they are dependent on each other, they are coupled, okay, so they are not free. So you can derive one coordinate if you know another coordinate, that is possible, but then it is not independent of that coordinate. So that is one of the difficulty. And then the forces of constraint are not known a priori. That means we don't know what are the forces that are acting on the constraint. We have to define them, we have to solve them, we have to find out the unknown content there, the additional factor that acts there. Okay. So if you have already studied about Lagrangian and Hamiltonian, which we are going to do in the next unit, Lagrangian Hamiltonian helps us to know these forces of constraint. So these forces are not known to us. We must find them out mathematically or analyze them and solve it. Okay, and this is important. So these are called the constraint difficulties, and there are different approaches to actually solve these constraint difficulties. Very important. Next is generalized coordinates, and I would prefer stopping at this particular topic. Okay, generalized coordinates. So generalized coordinates in general, I think you already know, because this is very much a part of your UG syllabus everywhere most of the times. So if you consider without a constraint, a system is moving. Let's say one particle is moving without a coordinate. It basically can move in the x, y, and z direction, and it will basically have three degrees of freedom, right? We already know that. But then if you are considering n particles, then the number of degrees of freedom will be that many fold. So that means it will basically have 3n degrees of freedom. So degrees of freedom, I think we already know. I think this is a common example given by most of the teachers in schools and colleges. I think this is a very simple idea. You go to a junction, and then there are three ways, right? You can go either this direction, this direction, this direction. So if you are at this particular point, you have got 3 degrees of freedom. Okay. So this is what is meant by degrees of freedom, right? In general, very simple example, might not be always applicable, but then it's okay. But then if there is a constraint, that means let's say there is a no entry on this direction. That means if you set 3 now, it's not 3, it is 3 minus 1 now. So that is 2. You either can go this way or this way, because the other side is no entry. I've seen this example given by many school teachers and college teachers, and I think this is perfectly fine. It works, okay? It works for a basic understanding. So this is if you have k constraint, if the degrees of freedom for n particle is 3n, k constraints are applicable there. So the degrees of freedom will reduce to 3n minus k. So if the degrees of freedom reduces, that means the number of dependent coordinate also reduces. That means the number of equation reduces. That means the problem becomes simpler. And that is why generalized coordinates. That is why generalized coordinates. Okay. So with holonomic constraint, one can introduce 3n minus k independent generalized coordinates. So understand the word independent. That is why I've just made it bold. Okay. All these coordinates will be independent of each other, defining them separately. You can have n number of equation, okay, or sorry, 3n minus k number of equation instead of 3n equations. So that means the number of equation has reduced. It becomes easy now, okay. So you can have these equations now, r1, r2, r2, up to rn. Let's rn n number of equation. If you have n number of equations, you can solve it for n number of variables. Okay, and then you can find out all the dependencies, all the forces, okay, all the dependencies of the independent generalized coordinates and so on. Okay, you can write down an equation. Okay, write it down in the form of an equation. It might or might not depend on time, not mandatory, depends. Okay, so if you consider this coordinate here, you have got 3n minus k coordinates. So 1, 2, 3 up to n, 3n times it will go minus k plus 1, because there is a time there. So there will be an additional coordinate there. Okay.